Hello once again. Glad to have you all back. We are going to talk this week about telescopes. It's our last unit before we start talking about things out in space. Next week we'll talk about the sun and then on to the stars. In this first mini lecture, we are going to talk about optical telescopes, those telescopes that operate in visible light. And in the second mini lecture, we'll go into telescopes that operate in other wavebands. If you remember a few weeks ago, we were talking about the electromagnetic spectrum, and we talked about how only certain portions of the electromagnetic spectrum can get through Earth's atmosphere. Obviously, optical light can get through Earth's atmosphere. It's why we can see the sun and the moon and the stars, and each other for that matter. A tiny bit of ultraviolet light can, some near infrared light can, and most radio wavelengths can. So most of the astronomy observations that are done from the Earth are with optical light or with radio light and a little bit of infrared light. Most of the rest has to be done from space. Before we talk about those telescopes, we need to begin with some definitions. And these definitions deal with angular size. So when you look at someone across the room, they look quite small, and the reason they look small is not because they are short. They're not just a couple inches tall. The fact is that what your eye actually measures is the angle that the person takes up in your line of sight. And so the further away they are, that angle changes, that angle gets smaller, and the smaller they look. Whereas if they're right up in your face, they can take up your whole field of vision. So most of you are probably familiar with the measurement of angles known as degrees. There are 360 degrees in a full circle, and if you hold your thumb at arm's length, that's about 1 degree, a little more than 1 degree. The full moon is half a degree across, so that gives you some idea of those sizes. Astronomers use two units of angles that are smaller than degrees. The first one is an arc minute. So if we take 1 degree and divide it into 60 equal parts, each of those would be called 1 arc minute. And 1 arc minute is about the smallest thing that your eye can see. If you've got 20/20 vision, that's about the limit of what you can do. And here it would be the width of a thumb from about 100 yards away. So imagine someone across a football field giving you a thumbs up. If you look hard, you probably would be able to see that thumbs up, but not much detail of it. However, in astronomy, an arc minute is still a fairly large angle. With telescopes, we can see to much smaller angles. So you can imagine if we take one of those arc minutes and divide it up into 60 parts, each of those will be called an arc second. And an arc second is tiny. It's about the width of a thumb as seen from 3.5 miles away. So arc seconds are really small. Our atmosphere blurs optical light, as we'll talk about in a couple slides, and for most telescopes the blurring of the atmosphere is somewhere around 1 arc second in size. So from the ground, typically 1 arc second is about the smallest thing we can see with a telescope. Telescopes are the instruments that astronomers use to collect and analyze light. There are several different types of telescopes, and we'll talk about a couple of those in the next few slides. Here are pictures of two telescopes. The one on the left is the Lick Observatory telescope. It's 36 inches in diameter. We always refer to telescope sizes by their diameter, not their length. And for scale, you can see a person there at the lower left. The telescope on the right is one of the world's largest telescopes. It's the Keck telescope. Its mirror is 10 meters across. That is roughly 32 feet across. And you can see for scale there is a person down at the very bottom of that mirror. There are two main types of optical telescopes. The first one is called a refracting telescope, and you can see a refracting telescope here at the top. A refracting telescope has a lens at the open end, the end that looks up at the sky, and then an eyepiece or a camera at the other end, and the lens bends the light to bring it to a focus down at the eyepiece. Refracting telescopes can allow you to get very sharp images, but they aren't used very commonly in today's day and age. The reason for that is that this lens up at the top can only be supported around the very edge of the piece of glass. If you try and put any support behind the glass, you block the light. And if you get a lens much larger than about 40 inches in diameter, then that lens will sag under the force of gravity and you won't get a sharp picture. Not only that, but the sagging is different in different parts of the sky. There's no way that you can build a lens that will correct for this sagging. Because of that, most telescopes these days are reflecting telescopes, and one example of a reflecting telescope is shown at the bottom. The end of the telescope that points at the sky is open, and light comes in from a star down to the bottom of the telescope where there's a mirror. The mirror reflects the light back up to yet another mirror called the secondary mirror, which then can send the light off to the side, or sometimes it will send it back down through a hole in the bottom mirror where it comes to a focus. And so here you can have your instruments or your eyepiece of the telescope. Because the reflecting telescope supports the mirror from behind, you can build reflecting telescopes arbitrarily large. And so that's why all the large telescopes in the world today are reflecting telescopes that use mirrors. So refracting telescopes means to bend light, and that means you have a lens. A reflecting telescope is a telescope that uses a mirror to reflect light. The main purpose of a telescope, and the reason that we have different sizes of telescopes, is to gather as much light as possible. That the larger your mirror is, the more light you collect at once, and so the less time you need to see something faint. And since the amount of light coming in depends on the area that you are collecting it, then it's really the area of the mirror that matters. And so, since most mirrors are circular, here are some schematics of telescopes in Hawaii and their relative sizes. You can see that because most of these mirrors are circular, the area will be pi r square. And so if you double the radius, your area goes up by a factor of the radius squared, or 4 times. If you triple the radius, then your telescope is able to gather 9 times more light. And so between the smallest mirror in Hawaii, this one here that's 0.6 meters in diameter, and the largest ones, these Keck mirrors that are 10 meters in diameter, there's a difference in light gathering power of almost a factor of 300. So what would take you 10 minutes to get a picture of with this telescope, you could get that same picture here at the Keck telescope in just a couple of seconds. There's a weird property of light that whenever it goes through a hole, such as the hole in a telescope or the hole in your eye, it begins to spread out on the other side. This is called diffraction. And the size of diffraction depends on the size of the hole. The larger the hole, the less the light spreads out, the less the diffraction is. So the same thing happens with telescopes. With a small telescope, such as that you might buy at Walmart, the light spreads out enough that the picture that you get at the other end may only have details of 4 or 5 arc seconds, which is a pretty small detail, which is why you can see more with a telescope than with your own eye. But it's a lot worse than what the atmosphere would allow you to do. So if you go up to a large telescope, you can see much sharper. The theoretical limit for the Keck telescopes in Hawaii is that they can see 1/100th of an arc second. However, if you remember from before, I told you that the atmosphere smears light out to about 1 arc second. So if we don't do anything else, then building telescopes larger than about 1 meter in diameter doesn't allow us to see things any sharper. However, we now have tricks that allow us to correct for the bending of light by the atmosphere.